Hi, everybody. We have the pleasure of welcoming Hans Dembinski this time to talk about automatic differentiation with JAX. So he's probably very well known for other things such as boost histogram. But I'll let the show to Hans, who navigate us through this 1 hour tutorial. Thank you for coming.
Hey, thank you for inviting me to give this talk. Yeah, so this is about JAX, where I'm not really an expert myself, I must say, but I think I can give you a tour anyway. And that's a good thing. It's not a very complicated module, so it's easy to learn. All right, so let's go on. So what is JAX? Yeah, it's a module that allows you to do transforms basically quite generally of vector valued functions. So everything you can normally express in NumPy code that maps from some real numbers vector to another real number vector. It doesn't have to be the same dimension. And what this means is, I mean, this is the general thing it does. And in particular, one of these transforms is to compute derivatives. It can do this automatic differentiation that we will look into here. And this you can use to compute a gradient or a Jacobian or a Hessian. And it also is able to use this technique to JIT compile your code. So similar to Number, but it uses a different kind of intermediate language, this XLA compiler, which in the end, as far as I understood the docs, produces then, I mean, it also uses LLVM to run, to generate machine code. And this machinery here is also used by TensorFlow, Julia, PyTorch, and a program called NX or library called NX. Yeah, and it can also, for that reason, vectorize the code. So if you have an expression that you can apply only on one matrix at a time or something, but you cannot easily vectorize with NumPy, this also has some functionality to apply it then to many different matrices or many different vectors in a row. But I will not talk about this part. So I will only talk about this first part, automatic differentiation. It's the successor of another package called Autograd. So if you used that before, you should be at home. It mirrors the NumPy API, which I find very nice because then, I mean, if you already know NumPy, then it's easy to use this. And it's powered by Google, so it's not a small project. This has big industry behind it. So why do I like JAX? It's easy to learn if you already know NumPy. It's really laser focused on this one task. I like libraries like this. I'm author of a few libraries like that myself, because I think there's great power in this building complex solutions out of low-level simple building blocks. Yeah, like this, like it looks like this building was built anyway. Yeah, okay, anyway, and it's supported by Google, so you don't have to worry about this being unmaintained tomorrow. Is this going to be a replacement for Number? No, not yet at least. We'll come back to that. So I built this talk here based on very nice online tutorials that are already out there. So if you want to know more or go more details, I can really recommend this general introduction here by Boris Settinger. So you can just follow the link. So it's a Python notebook, Jupyter notebook with animations, and it's really nice. Then there's also here this paper, which is a survey of automatic differentiation and machine learning. That is also very nice. And then finally, also JAX documentation is really recommendable. So it's both beginner and power user friendly. So they have lots of tutorials. It's really a nerdy library in a way, but they always make it so that you can easily follow, so even the more complex topics. All right, so let's start with derivatives. So yeah, I mean, derivatives, why do we care? They are in statistics everywhere. So when you want to do a minimization of some function, like mean does, for example, then you have to basically iterate this Newton-Raphson formula here, and there you have two derivatives, the first one and the second one. So you need to know these to actually do this here. Another place where this pops up a lot is when you do error propagation. The classic error propagation, you have your covariance matrix and some dimension x or along some vector x, And then you do some mapping from that to some other vector in general. And then this, this mapping, you can then compute the covariance matrix in this new vector y with this formula here, where you have to put in the Jacobian matrices where you derive each y to each x. So in both these cases, you can, it's nice if some computer program computes the derivatives for you, so it's not tedious. So how do we compute derivatives? Yeah, I mean, basically derivatives given by this limit here. So you take your function at x plus some tiny h, you subtract your x, and then you divide by h, and the limit of that with h to 0 for one dimension here is what you call the derivative. And when you have this more general one from Rn to Rn, then it looks maybe like this. So here you have to actually compute for each x, you have to do this here. And now x is a vector, and you use always one component of that vector that you wiggle around a little bit, and then you get a whole vector of y's out for each x. So if you put these all together, then you have your Jacobian. Yeah, sorry, I forgot to mention this. So, I mean, if you have slides during the talk, and please ask questions during the, if you have questions during the talk, please ask them. You can use Slido here. So you have to go to the web page and you have to type this number 19594 in the box, and then you can put your questions here, and I hope you will see them. So, yeah, then 3 ways of doing this on a computer is first is numerical differentiation. Then we have symbolic differentiation, and finally automatic differentiation. And this is kind of the best of the 3 if you want. So in some sense, but we will go into that. So numerical differentiation basically means you replace this limit here just by just a finite value of h, and then you compute this, and you know from Taylor expansion that this is then order h squared accurate. So if you make your h small enough, then you can neglect this other term and you have your derivative. Great. By the way, this is not how it's normally computed. In most cases, you want to have this symmetric formula here, which is more accurate. Okay, but if you choose your h too small, then you get numerical issues. So when you on a computer, if you write 10 to the 16 minus 1, this is exactly equal to 10 to the minus 16. Not true in reality, but on computer, yeah, it is. So this is the problem: how to choose your h so small that that the remainder here is small, but not so small that you run into these errors here. The good thing about this method is it works on any function. So my f could be anything, could be some C++ code that I wrapped in Python, whatever. So, and it's also not too bad in terms of computational cost. So you need 2 times m, where m is the dimension here of the space, function evaluations when you map from Rm to Rn. Yeah, okay, you could say also in theory there's also here the n there somewhat, but I count it like this, that a function evaluation of an n-dimensional f is I count only once here. Okay, so the contrasts are like what I already said. So to choose your h optimally is really difficult if you don't know anything about your f. And there has been lots of research and figuring this out, but it remains a complicated and fragile topic. So it works often enough, but yeah, it can also fail catastrophically which you all know if you have used Minuit, which uses this basically. Yeah. And most of the failures are because of this. So, okay, and what it also gives you, it doesn't give you a lot of very accurate results. So the accuracy often is usually well below the machine precision. It's something like square root of the machine precision. Okay, so yeah, this is all about numerical differentiation, I want to say. Then the next thing is symbolic differentiation. So this is what you do on paper. We know all the rules, how to compute derivatives, right? Yeah, it's purely mechanical. You don't have to think about it. There's no art in doing derivative differentiation as opposed to integration. So you can teach all these rules here to a computer algebra system, for example, SymPy, and then you can ask SymPy here to compute the derivatives of this formula. By the way, I like SymPy a lot. I use it a lot since I learned it. It's very easy to use. I can only recommend you to use this if you ever need this. And it's in Python. Yeah, so this is great if you need to know the formula. So then, and also when you can also use SymPy to generate the formula and then turn this into NumPy code, and then you can compute this derivative many times very efficiently. So this computation here is actually slow. I mean, SymPy is completely written in Python, so it's not doing this very fast, but the output it produces, it can then be very fast. So when you put in new numbers in the same derivative formula, then this calculation can be fast. And it's exact, so within machine precision, so we don't have this problem as we had before. And okay, but the big downside, the caveat is this only works when you can actually express your function here as a code like this, like write down mathematically on the paper. So it has to be analytical and symbolically representable. Doesn't work for your typical computer function that you just write in Python, yeah, where you can have things inside like if and while, and then how would you put this in here? No? Okay, so this brings us to the final thing, which is kind of the best of both worlds, you know, in a way. It's this automatic differentiation. So this is an alternative approach to compute derivatives using hyperreal numbers. So that sounds really cool, right? But yeah, so hyperreal numbers is an extension of the real numbers as a numerical field, and you include here infinite and infinitesimal quantities. Okay, that sounds maybe scary, but it's actually not so complicated. And we physicists have used this mentally a long time. The only thing is that mathematicians really figured out to do this in a rigorous way, and they can prove that all this stuff works. Yeah. And the other good thing is you can implement hyperreal numbers easily on a computer. And then any calculation that works with a real number will also work with a hyperreal number. Yeah, okay, that's what I said. So this works on any function in principle that you can write in code. It's exact within machine precision. It has about the same cost as numerical differentiation. So yeah, maybe, well, yeah. And the caveats are, so you still have a problem if you use this in Python. If you have some code that is running in C++, it will not be able to do this because the Python code cannot look inside the C++ code to follow the hyperreal numbers through. But you can also use this in C++ code itself. And maybe you can link the two regimes even if you're smart. But okay, we will not talk about such things. So before we go, yeah, I mean, I want to motivate these hyperreal numbers because when I learned about this, I thought it's a really neat thing. So if you're a little bit of a nerd, you might like this. So the idea is here you start with Taylor series. So when I displace my x here by a small epsilon, then I can compute what this result is going to be. In the Taylor series, it's going to be my f of x, and then I have the first derivative here times epsilon, and then some higher orders of epsilon. So now I do a trick. I just define that my epsilon squared is 0. I can do that. It's my epsilon. And this then truncates the series to an exact result, namely this one here. And you observe here maybe already that you can now read off your derivative here as the thing that's in front of your epsilon. So if you somehow manage to put this f of this x plus epsilon, if you can somehow put that into a calculation, you will get out the derivative as a side product here in front of your epsilon. Yeah, and yeah, this is what I said. So you should really think of hyperreal numbers analog to complex numbers, where you also you have an extension of the real line here with this complex y times I, and here it's y times epsilon. And instead of epsilon squared gives you -1, you now have the rule that epsilon squared gives 0. And then in the complex, for the complex numbers, we have this function here, RE, that gives us the real part of a complex number. And these hyperreal numbers, they have something similar that's called standard, which gives you the standard part. So it also just extracts the real number from your hyperreal number. And then you can do calculations with this. So It's actually very easy now, based on this rule alone, to derive laws for addition, multiplication, inverse, and power. This is how addition looks like. So, well, I think it's straightforward. Multiplication, here you have to, well, basically calculate it all out and then throw out the epsilon squared. Then you get this on the right-hand side. Also directly follows here from the principles. And when you have a division, then you do what you also do for complex numbers. You have to expand the numerator and denominator, and then you get the result. And you take things to the power, then you just have to do the multiplication rule many times, and then in the end you come out, you will find that it's this formula here. So all this follows already just from the definitions. Yeah, okay, and once you are at this point where you can do multiplication, addition, and potentiation, you can compute polynomials of any order, including polynomial series up to infinity. And this means you can now also compute derivatives for transcendental functions like the sine and the cosine and so on. So basically you can compute everything now. And you can also put these rules into the computer. And then any code that works on real numbers also works on hyperreal numbers. And as I said, derivatives are computed automatically as a side product of this calculation. And this now also works if your computer code uses things like if, while, and so on, because in the end, what you do when you do if, while, and so on is always, you can always break it down into these elemental operations where you just add things or multiply things or whatever. All right, that's basic introduction into automatic differentiation. Now, is there any questions on this part? Otherwise, I will go to the tutorial, to the live tutorial. I see no hands. You can also use Slido, as I said, to ask questions anytime. Okay, so I mean, when you use JAX, you don't see anything of this fancy hyperreal numbers anymore. Yeah? So if you couldn't follow this, or if you don't care, you don't have to. I mean, this works all very easily, even if you don't understand this. Okay, so this is how, so you have to download JAX, of course. You also have to download, I don't know why they do this, but you have to manually download also JAX-lib. So if you want to use it, you have to download both these things. And then if you want to follow this notebook here, you also have to download these other things here.
Hans, just
yes?
Can you make it a bit bigger?
Yeah, right. I will try and do that.
Just one plus or two, that should be enough. Yeah, that's much better. Thanks.
Is it all okay like this?
Yeah.
How are hyperreal numbers represented in the computer? Yeah, it's basically similar to a complex number, right? So complex number is also just two real numbers that you put together in space and in memory. And then the computer has all the rules that I just talked about. They have them implemented. So when you add two hyperreal numbers, they add them, yeah, they add the real part and they add the other part in front of the epsilon. And when you multiply them, they apply this rule and so on. So all these, you can actually, so if you look into the tutorial that I mentioned on slide 3 or so by Boris, he really shows you how to write a hyperreal number by yourself. So you can even implement it in Python by yourself. So we won't do this, but it's really easy. Okay, so some few other things. Here in JAX, we use NumPy a lot, so you have to import the NumPy library here from JAX. So it has the same API, or almost the same API as NumPy, but it works a little bit differently internally. So this we call JNP here to distinguish it from the normal NumPy, which you also need. You will see later why. I mean, firstly, JAX doesn't cover the full API, and even they recommend that you use a normal NumPy for some things. I also import here NumPy here, but I will use that later. So you don't need that for JAX and Matplotlib also just to plot things. So if you want to work with double precision, then you also have to explicitly enable this. So by default, JAX doesn't do that. It does float precision. Yeah, and then okay, here you can see which JAX versions I have. So it's fairly early, but I think the API is still quite stable. We also use number is also 0 point, but nobody cares. Okay, so let's start with simple function. So I put in here just a simple polynomial, and I use JAX. I ask JAX to compute the gradient of this function. So nothing happens because this is just it's evaluated. I mean, you don't put we didn't give an argument yet. And JAX evaluates everything lazily. So only when we actually call this with an argument we see. So here at the value at 1 is 5, and now it finally computes here something, and it tells me that the gradient is 6 at the same value. And yeah, this complaint here is because I don't have a GPU, so it does the computation on the CPU. But if you have a GPU, NVIDIA type or TPU even, then it would compute there. All right, so that's also why it uses these device arrays. This is just a way, I mean, they want to keep the memory on the GPU as long as possible. So only when you actually print things, then it will fetch it back to the computer. Okay, so let's visualize this. So then maybe you don't trust me that this is the correct derivative. So I wrote a little code here that shows you that it indeed is the correct derivative. So here I plotted this function from before, and also the tangents, which are given by the derivatives at various points. So this works, great. Yeah, okay, I can also evaluate this, of course, at another point. So here's when you don't put a real number in here, but an integer, then you get the first error. So JAX is really particular about convergence. So by default, it wants you to pass really floats and not integers. Okay, so you can also, I mean, your f, because it's written in this general way, I can also put in an x that is an array now, and it will work anyway. It will calculate things element-wise. And if I try the same with the gradient, I get an error. Does someone have an idea why this is an error? I mean, I said before that JAX can compute this fine, derivatives also from vector valued functions. It's a little bit of a mean question. The answer is up here in this line. Can you say upfront that you run on CPU? No, I don't know. So maybe yes. If you know a way how to do this, let me know. I don't know how to avoid this warning here. I mean, you can artificially suppress it with a warnings filter if you want. Okay, so the thing is, I asked for gradient here, and I can only compute the gradient of a function that gives me a single number as a return value. But now, since this is doing this element-wise, I now have a function that maps from R2 to R2. So gradient is just the wrong function to use. Okay, that's why this doesn't work, but it's easily fixed. We just have to say, I want a Jacobian now. And this is what this function JAC forward does. There's also JAC-ref. So now if I use that, then I get my Jacobian matrix just fine. So there's JAC-ref as well. This we can also use, gives the same result. So why are there both of these? You should use one of them. Well, for most cases, I think if you actually want to compute the Jacobian, you probably want this one. There are situations where this is more efficient, and that's the case when you map from a high-dimensional space into a low-dimensional space. So if the M is lower dimensional than the N, then JAC-ref is more efficient. So if you run into performance issues, you might think about the difference. But for simple playing around, I would always use this one. This is also what they recommend. So if M is equal to M, they also recommend this forward one. Okay, so now let's maybe use a more interesting vector valued function. This one here. No, sorry. So this is this goes now more in the direction of how we actually compute derivatives. So we have We have our cost functions in statistics where we have n-dimensional input, but then we have only a number that is the output. Yeah? And this I mimic here with a very simple function where I have two numbers and I compute one number. So it's a bilinear form. And let's try to compute the gradient of that. So I take again this x from before. So yeah, my g works, but when I try to compute g prime, this doesn't work. Okay, you get a lot of output, but it's really nice that they tell you what actually happened. So so we don't have time to read this, but the point is, what we did is we just naively took our numpy function here, which has numpy dot in here, and that doesn't work with JAX. So we have now to replace np dot with the equivalent function in JAX. This is what I did here. And then it still doesn't work. So why doesn't it work now? It says dot requires any array of scalar arguments, but we got a tuple. So this is again the thing that JAX is really strict about, not converting types. So numpy dot works if you put a tuple here, but JAX really wants us to put an array here. Okay, let's use an array. I use a numpy array here, and now it works. Now you could ask me why I didn't use J and P array here. That also works, but the official recommendation is to, when you have constant arguments, you should use numpy. And when you have dynamic arguments, like here, the x is a dynamic argument, you don't know what this value is, but you know this a that is fixed, then you should use this J and P. So that's a rule. You can also compute the Hessian now of this thing, and it gives the right answer. Yeah, this is just the rule I just mentioned here. So this is not what I made up. This is what they say in the official documentation. Okay, so what happens when your function has several parameters? So I have a function here, f of x and a. So what happens when I compute the derivative? Yeah, it computes the derivative always by default with respect to the first argument. So the a is not, there's no derivative with respect to a. But you can change that, so there are more arguments to grab, and you can make it derive also to the second argument or whatever. So I would refer you to the docs. Okay, so now I want to show you some things that are unfortunately not so nice. So I imported from NumByStats my normal CDF function. So this is the CDF of the normal distribution. Now I could get the idea that I want to compute the derivative of this to get the PDF back with JAX, and this seems to work. But we saw before, I mean, it only actually happens to fail when you call this with some arguments. So CDF works because I imported it directly, and the PDF doesn't work. And the reason is what I explained before. So JAX doesn't, I mean, since this is number compiled, so JAX doesn't see the Python code here, just sees the JIT compiled function and cannot look inside, and therefore it cannot compute the derivative here. So I have to actually re-implement this in some code that JAX can understand, and only then it can compute the derivative. So there is a way actually to teach JAX about new primitives. So if I have some function where I know the derivative of, I could in principle teach JAX about it. But this is too complicated, I think, to cover here. But it's explained in the docs, and there's also a tutorial about this, so I will not cover this. And then there's another, so this is rather complicated. So this is really, I don't know, the expert level, I would say. But there's also a simpler way of teaching JAX about some derivatives. When you can implement that derivative in JAX code, then there's a simple way to do this. You don't strictly need to do it then, because JAX can compute the derivatives then already. But you may know a better or faster or more accurate way of computing the derivative than JAX can figure out with this hyperreal numbers. And there are ways to help it out. So, but this I would also consider more expert level. So normally you don't need to do this, I hope. I mean, I didn't run into the problem yet that I had to do this. But if you run into this problem, there's a nice tutorial in the JAX documentation how to do this. And it's fairly easy. Okay, so that's the general first steps parts. Now I would talk about some practical examples. Do you have any questions up to this point? Is it too fast or not too slow? Still have half an hour. Ah, okay, someone gave me the thumbs up, so I think I should just proceed. Okay, so now, okay, yeah, we want to fit a Gaussian model to histogram. We use Minuit for this, and this will also do some benchmarks here to show you how much you gain from computing derivatives. So Minuit can, if you can pass a derivative to Minuit, then Minuit will use that, and it can actually accelerate this minimization. Okay, so as I said before, we now have to implement our CDF and by ourselves so that JAX can derive it. And I need the error function to do this for a normal, the CDF of a normal distribution. So this is the formula here. So I just implemented that. And since I used the error function here from JAX, it can also compute the derivative of that. Okay, yeah, so I generate here some random data, some histogram. I define my CDF here because I want to fit a histogram. So you do with CDF, and then I define my negative log likelihood here, where I strip the constants. And yeah, this I also have to write in plain C code. And here I take again, yeah, here I first compute all the probabilities over my edges of my histogram, and then I compute the probability content per histogram with diff. And this is an extended likelihood, so I also multiply this here with an amplitude. And then this is this usual Poisson stuff that you have to do. And here I put in here some numerical trickery so that this doesn't give you none when either mu or n is 0. You can also do this differently, but I do it like this. Okay, so that this is the setting, and now we try to fit this in several different ways with Minuit, using gradient information or not using gradient information. So this code here just is running Minuit. So we use strategy 0 here. This is maybe something good to know. I don't know whether you ever played with the strategy of Minuit. If we set this to 1, then it does more computation than necessary, but it gives you the Hessian matrix for sure, an accurate Hessian matrix. But here we are not interested in the Hessian, we just want to compute the best fit value. So that's why we do it like this. Okay, yes, and yeah, my thing has 3 parameters, amplitude, the mean, and the sigma. Okay, so let's run this. Okay, I forgot something. I forgot to actually execute this. Okay, this seems to work for the general case where I don't use the gradient at all. Also works when I put the gradient. That's good to know. Actually gives exactly the same numbers here, but you can see now it only used 26 function evaluations instead of 66, but it used 6 times the gradient. Okay, that's cool. This is, by the way, not necessarily so that you get exactly the same EDM and function value here. Now I run this. Yeah, by the way, I didn't talk about the JIT compiler yet, but here we will also use the JIT compiler. So this here was just computing gradients. Now I also JIT compile the function, but I don't use number for that. I use the JIT compiler of JAX. But the gradient I leave not JIT compiled. So this should give us hopefully the same result. Actually, there's a little bit difference here because compilation probably introduces some optimizations, and then you don't do exactly the same floating point math, and that's why we have some minor deviation in the EDM value. But basically it's the same, so the same number of function evaluations. Okay, and finally we JIT compile everything, also the gradient. Okay, so let's compare these things. So this all works, that's good to know. Yeah, for comparison, I also use Numba now, another JIT compiler. Here I don't have the gradient information, and just put this in here for reference. You see later that this is actually interesting. So now we want to do some benchmarks. So I run this many times. And this is the result plotted. So this is rather interesting. So yeah, when you use the JIT compiler of JAX and the gradient information, then you get a really fast result. So this is, I mean, this is always with respect here to the fastest. So the fastest in fact is NumPy. So the NumPy JIT compiler is just better than the JAX JIT compiler, even though they use LLVM at a low level. I don't really understand that. I mean, normally you would think that the JAX thing should be as good, but apparently NumPy has some tricks up its sleeve that JAX has not learned yet. And note, I mean, it's faster than JAX even with the gradient. So it doesn't use the gradient information, it's still faster. So for now, yeah, okay. So this may you now think, why did I listen to this guy? It doesn't work. But I mean, here I have a really simple function with 3 parameters. If you have a function that has 100 or 1,000 parameters, then you really, really want to use the gradient, because then this will speed up the minimization a lot. So yeah, don't be disappointed by this. But I thought it's interesting to see anyway. Yeah. Okay, then the other things are not so surprising. So if you just use the JIT compiler but you don't use the gradient, then you get a boost of factor of 2 maybe. So that's nice. So the JIT compiler does something. If you don't JIT compile at all and you compute this with the gradient, it's actually slower. And that's the reason for that is that this gradient computation, even with automatic differentiation, is quite costly. And you really need this JIT compiler to simplify that computation and join it somewhat together, and then it's going to be fast. So bottom line, if you compute the gradient, you want to have high performance, always also JIT compile that. So there's a question, is it correct that JAX does not interoperate with NumPy, which is mimics its API? Yeah, that is correct. So yes, so you cannot, I mean, you might be able I mean, here you see it already. I mean, if I did not import here my error function from JAX, and okay, but the code here looks exactly the same. So if I would write this with SciPy and with NumPy, I would get the exact same implementation. I just have to make sure that I import the error function here from JAX instead of SciPy. And likewise here before, so if I write if I've written some function that used NumPy, the chances are very, very high that I can just replace all the NP by JNPs and then it will work. So that's what I can tell you, but it will not work with any code automatically. Okay, yes, coming back to this. Okay, I think I said all that. Yeah, you can also now try to compute the error matrix with JAX. So, I mean, Minuit computes that for you, but you can as well just compute it with JAX, and you compute the Hessian, and then we have to invert this, and then this is the covariance matrix. If your function was a negative log likelihood function, then this gives you exactly the Hessian matrix. If it's least squares function, then you have to either multiply or divide by factor 2. I always forget which way around. Okay, so, but the good news here is you get exactly the same errors out when you use JAX. So in principle, this JAX Hessian is of course much more accurate than the one computed by Minuit. The nice thing about Minuit is since it's using numerical derivatives, it works for any function. It doesn't have to be JAX differentiable. Okay, we can also ask which is faster. So when we let this Minuit do this many times, so it takes about 130 milliseconds per run. JAX is a bit faster here, so about twice as fast. Yeah, but this is so. Yeah, so if you want the additional precision and you have already something that is JAX differentiable, then this may make sense. Another thing is, so if you really, so here this is kind of a fair comparison, because normally you have to, right, you write your cost function, and then it's a one shot. So for this one problem, you have your one cost function, and then you want to just evaluate, you want to fit it, and you want to get your errors out. So in that case, there's some kind of compilation cost in a way that JAX has to do to figure out the derivative. And you cannot amortize this over many evaluations of the derivative. If you can actually do this, so if you want to compute the Hessian not at one point, but at many, many points for some reason, then JAX is much, much faster in doing that. So this is the second benchmark that I do here. So here I took out this compilation cost. I call it in quotes compilation cost. Yeah, and then it's much, much faster. So this is now less than a millisecond, third of a millisecond. But if you include the compilation cost, then it's very slow, or as slow as mean it would be. Okay. So any questions up to this point? 20 minutes left, which should be enough. Okay, then I move on to the last part. So this is now another practical example. You may know this if you use root already, they can do this internally, but if you don't use root, you have to implement this yourself. So let's say you have a fit where you have uncertainties on the x and the y, and you want to fit this, and then you are in trouble because your normally square slang doesn't allow you to include errors on the x-axis. And then there are hacky ways of doing this, and less hacky ways, and a less hacky way that's actually reasonable and founded on some theory at least is this way here. So you say, well, if my sigma on x is small, then I can use my Taylor expansion here to compute what would be the equivalent error I would have on the y-axis from the fact that my x value is uncertain. And then I can compute my least squares cost function here that I take my values here and I subtract the model. And here I take the y error and then this propagated x error that is also now y error after the propagation. But now I need the derivative of f. And that's a good place where we could use JAX, right? At least for simple cases. And this is what I did here. So I have a polynomial model now that I want to fit some xy, scattering xy data. And now I generate this. Well, this I can straightforwardly. So polyval is a NumPy function, but there's an equivalent JAX function here. So this is easy to implement. I can take my gradient here and compile it. I can check that this gives me the right answer. Then I generated some toy data here, and I plot this also so you can appreciate it, how it looks like. So this data scatters now in y and x according to these error bars here. That's why you can have outliers that are far away like this one. Okay, now we have to write our cost function again, so that JAX can differentiate it. Well, okay, this is actually optional. It's also good to work without. Yeah. Okay, but yeah, I did it at least. So also to have it compilable. So this is straightforward, it's just a function that I wrote above in the math I implement here. And then I have to tell Minuit that this is a least squares function now and not a negative log likelihood. And I can evaluate this works, great. And then I run Minuit. And it also gives me a result and also some nice errors here. And then we can look at this solution that Minuit found. And yeah, this looks fairly reasonable. And if you calculate the chi-square, it's really a good fit. So this works. If you would have neglected the x errors, you would have gotten a terrible fit, I can tell you. And maybe also the line would look a little bit different. All right, that concludes my presentation of JAX. Do you have any other questions on that?
Thanks very much, Hans. Let's see. A few hands. Jake?
Ah, yeah, Jake, yeah.
No question for me. Just greatly appreciate your information.
Thank you.
Thanks.
Thank you.
Maybe one point, Hans. I know because you had mentioned that you have been using JAX for some real daily problems and issue and work actually. Maybe you could share some thoughts on that, because it goes beyond the examples to something that really scales up probably.
Yeah, no, so I have not really used this. So a colleague of mine actually had this problem that they wanted to fit X and Y error data like this. And then I told him about this solution. So he used that, but I didn't use it myself yet. So for LHCb analysis, I so far use minute without gradients. The problem is really for me that, I mean, it's comparably easy to, or I'm focusing now more on using NumPy everywhere. And as you have seen, NumPy doesn't play nice with JAX. And ideally, at some point, hopefully JAX JIT compiler is as good as NumPy's, and then it would be great. You get everything, no, for free. But right now, I think it's not there yet. But I think there's potential there. I mean, I don't see a principal reason why this should be worse. And it's Google behind, so they want things to be fast. I didn't put this in here, but they just won some benchmark where they were faster than anyone else. And this benchmark is some machine learning stuff. And there they use JAX also. So, I mean, they definitely have an interest to make this fast. There's a new question. Can JAX deal with variable length arrays, or do the arrays need to be fixed dimensional? Yes, that's a good question. So yes, only fixed dimensional ones are allowed. But I mean, no, in practice, I mean, the X that you put in, this can of course be any dimension, as we have seen before, right? So I mean, your X here, I can put in a number or two-dimensional or three-dimensional. This will work always. But if you have somewhere, if it's not upfront clear what the shape of the output array is going to be, so if somehow the shape of the output depends on some input parameter, then it doesn't work. But this is not usually the case we have. So usually we have the case where we know exactly how the dimensions map.
If you like, I could add to that question that there's an ongoing project in awkward array to make awkward arrays work with JAX.
Cool.
So the structure of the array with all its variable length lists doesn't change when it goes through the differentiation. You're just differentiating each element in it. And maybe we'll be able to do reducers as well, which would change the shape a little bit. But primarily, you're differentiating the numeric data in the array. We hope to support the variable length list case pretty soon.
Right.
So if I may comment and the question actually. So just as a comment, I think as far as I see JAX, there is also just also since people asked about production and so on, there is I think PyTorch as well, which is very similar, and TensorFlow, which is basically the same, like JIT compilation, automatic gradient, and all this stuff. And these, for example, we already use in production in, for example, setfit to do all these fits. So if you want to use that, and that comes with my question: do you know, Hans, maybe what the difference is of JAX, or what's the advantage, for example, of using JAX over something like TensorFlow?
Well, I think if you work already with TensorFlow right now, I don't see an advantage for you. So, I mean, in the end, they're basically based on the same idea, and this automatic differentiation is everywhere, and all these machine learning toolkits, they all employ this. So the only thing I like about JAX is it's rather easy to learn. So if you just have some simple code already in NumPy, then to use this is really easy.
This is the same as
TensorFlow. I just don't know TensorFlow.
Yeah, exactly. They also have this NumPy API like PyTorch as well, so it's a little bit like, it seems a little bit to me the same-ish. So I was wondering maybe you found a nice gel.
No, I think if you find a fan TensorFlow, then there's no reason to switch.
Thanks a lot.
All right. Any other question or comments that we have? Still have a bit of time, otherwise we stop here. Good. Don't worry, by the way, Hans, you were not fast. You went at the right pace. It's just that's what it is.
Yeah, so I planned well with the time. Yay.
You know, it's very, very, very good.
So if there's time, I had a question about how flexible JAX is. Basically, I'm kind of up and running with PyTorch, but one of the problems that I ran into is that I have a tensor that's differentiable with respect to multiple variables, and I wanted to dig into that and remove or stop the gradient according to one of the variables. But in PyTorch, I wasn't able to do that. How flexible is JAX in your experience in terms of stopping specific gradients?
Yeah, I think you can do that. So there's, for example, one function decorator that allows you to clip the gradient, so do not allow very large values. I think that's what you mean, maybe. So you could also clip it to some fixed value then, or something like that. So this is possible with JAX, yes.
Right.
I think you mean to stop gradient, right? So that the propagation doesn't go through the. Which
okay.
I think is a way. I don't know. I know in TensorFlow it's surely available, so I assume in JAX it's as well having the same. And I remember to have seen this functionality in JAX. Yes.
Yeah. I mean, like I said, so normally it differentiates with respect to the first argument of your function. But if you have, for example, well, if you have some first argument is something else, you can also say, don't use that, use another argument, or yeah.
Right.
So that works.
Yeah, so that does sound a bit more flexible than PyTorch.
Yeah, it's called JAX.lax.stopGradient. So it is there.
JAX.what?
JAX.lax.
Lax.
So it's called stop gradient, the same name as in TensorFlow. It's a JAX. You can use that as.
Okay, thank you.
Yeah, I guess there's some of the same people working on TensorFlow and on JAX. So, yes. It's of course inspired.
Well, thank you very much, Hans, again for joining and for preparing your tutorials. Always a fair amount of work. So I should say to everybody, likewise. Well, the GitHub is public. The link on the Indico page, so you can go and play with it at your own leisure and steal bits of code from there as examples.
Okay.
Right. And last point is we will have then the next topical meeting in a month from now, the first week of every month. So that's the 4th of April, I think, and that will be about PyHEP, which is our first example of a HEP-specific package for statistical analysis, whereas today was a more generic package. So if you're interested, just join as usual. So thank you again, Hans. Thank you again, everybody, for joining, and see you around.
Bye.
Bye, folks. Bye. Thanks.
Thanks.